Okay, so last presentation. Floods account for almost half of all natural disasters recorded in the last 20 years. And going forward with climate change, we expect to see more extreme flooding events, while at the same time seeing an urban population boom with an additional 2.5 billion people expected to be living in cities by 2050. Most of this growth is expected in Africa and Asia. Accurate flood maps help cities build resilience. Using high-resolution satellite imagery is a more affordable and less resource-heavy approach to developing flood maps than the traditional method, which involves teams of people on the ground collecting field data. Satellite-based maps can also be collected and updated more regularly, meaning fewer people are likely to be left off of flood maps, insurance plans, mitigation plans, and disaster response efforts. Cloud to Street was my partner for this project, and they are a small startup based in New York, focusing on using satellite imagery for low and middle income communities. Urban flood mapping has some inherent challenges. The spectral index that was developed to identify water in satellite imagery doesn't work very well in cities because of interference with the built-up environment, sort of shown here with this red rectangle. This is a flooded street, but there's just little pockets that are being picked up. Conversely, building shadow looks visually similar to flood and can be picked up when it's not actually flood. So these areas here in yellow are building shadow being identified as flood by a thresholded map. For this study, I used a digital globe Worldview 2 image of a flooding event in 2016 in Abidjan, Ivory Coast in West Africa. I focused in on two areas of interest. The first, up in the kind of center of the image, is Kumasi. It's a highly built up part of the city. And then the second being the southeast, which is more low-lying, less built-up terrain. Each approach, I looked at three different methods, so thresholding, sort of the traditional method, and then unsupervised and supervised machine learning. And each approach was validated using a reference data set that I developed in ArcGIS. For the thresholding method, I used sort of very well-known indices to identify water and vegetation, and then also explored some newer indices to identify buildings and building shadow, with the goal to sort of improve the thresholding result. The resulting map, with flood shown in blue, or all water shown in blue, and then building shadow shown in pink, has an accuracy score that's not great for Kumasi, about 67%, and then better for the less built-up region of about 79% in Southeast. The confusion matrix here shows where the model well predicts the true data. So if you see a strong signal on the diagonal, that means that the model is well representing the data. If you see a signal off of that, it means that there's some confusion. So here, you can see that true shadow is being represented as flood by the model. The next approach was supervised machine learning, and specifically using support vector machine, or SVM classifier. For this, I combined both sites, so I would have a more diverse and robust data set to then build the model. I used, you need this kind of big training data set when you look at supervised machine learning. I tried a lot of different inputs and eventually settled on these 6 parameters here, which is a mix of raw spectral bands and also spectral indices that I've been exploring. I tested and trained the data on 60% of that, and then validated on the remaining 40. The SVM map shows a little bit of a different perspective. It's a more continuous view of the flooding extent, and had an accuracy score of 93%, and the confusion matrix shows relatively minor confusion between the different classes. I also wanted to look at unsupervised machine learning, and so I looked at the k-means clustering approach. With unsupervised learning, you don't need a training data set, but you have to figure out what you want to put into it. What happens is the algorithm takes your unclustered data and finds similarities and clusters it accordingly. After testing a number of different inputs, I opted to just use the kind of straight, raw 8-band raster stack from DG, because I like the idea of not having to do a lot of pre-processing for this type of approach. I also looked a lot at the different number of clusters that I wanted to have output, and I settled on 7 as it minimized the confusion across land types, but didn't give me a whole bunch of extra clusters that weren't giving me any additional information. And each model was validated on a site-by-site basis. So this is the result. There's some pretty obvious confusion between water and flood with my nice hot pink ocean. But if you just focus on the city, it actually looks pretty decent. Most flood falls into one cluster and shadow into the other. And the accuracy scores of 84 and 79% are pretty decent for just throwing something into a model. but the hot pink ocean bugged me. And so I wanted to see if I could come up with some sort of combination of approaches. And so what I did is I changed the shadow cluster to a second flood cluster, and then applied the shadow mask that I developed in the thresholding approach. And this increased the flood-only accuracy score, so no longer trying to predict shadow, to 98 and 93% for each of the sites. Now, the accuracy score for shadow is 0, because I'm no longer trying to look at it. But visually, I think it's quite sort of pleasing, and it's a nice way of combining the different approaches. So the takeaway here is that machine learning offers a more accurate and a different perspective on floods than just the traditional thresholding approach, with similar or even lesser levels of effort. K-means is pretty simple once you get it up and running. Supervised machine learning was the best method for differentiating building shadow from floodwaters, if that's really one of the goals, but requires a lot of work in developing a detailed training data set. I dropped a lot of points on this ArcGIS image to make this work. Unsupervised machine learning provides a relatively low level of effort approach, but requires some interpretation after the clusters are defined. But there's a great potential, I think, to use these methods together to give you a clear picture of what the flood looked like. And more information means more people can be better protected and prepared for a flood. Huge acknowledgement to Jenny Palomino and Joe McGlinchey, who answered a gazillion of my questions on this, and also to Jeff Poe from Cloud to Street, who was my collaborator.